Dr. Cassandra Rauert, Cassie, is joining me from Queensland, Australia.
I have a long background looking at understanding human exposure to chemicals of emerging concern. So I suppose it's been the last 5-6 years that we've really been focused on microplastics. Do they get into our bodies? Do they translocate around our body? But the first step before we can understand exposure and then potential effects from this exposure is to get the measurement techniques correct. This propensity for false positives is a huge issue for pyrolysis-GC.
They'll say, we know about these lipids interfering with the polyethylene, but we've used an isolation method that we hope and expect to remove the lipids.
Also in science, you shouldn't expect, you should test. You should never assume that a method has removed a lipid. You should test it. Not many people are doing this. As you said, they just assume that their method is working.
If you don't have the central measurement correct, if those numbers are not reliable for microplastics in all of these different organs, which they aren't, all that other work is not any good. This is a bombshell. This is really forcing us to reevaluate everything we think we know about microplastics in the body, which turns out is really not very much.
It's irresponsible as scientists as well. Yeah, we want to be able to get the data right so that we can properly inform our health agencies, our governments, the general population.
So they say that it's actually really hard to measure microplastics in blood. Welcome to Roger Reviews. This is a very special edition. First of all, because I'm going to be going over the most important paper in this area, but more importantly, because I have someone joining me today to discuss this. So Dr. Cassandra Rauert, Cassie, is joining me from Queensland, Australia. And hopefully we can do an even better job of explaining the content of this paper. So Cassie, how are things there?
Great. Thank you for having me. Yeah, it's a pleasure to be here and talk about our work, our research. Thank you.
Excellent. Okay, so I definitely want to get into the technical aspects of this work. But before we do that, I wonder if you could just say a few words about why you picked this topic, how you got into this research project.
Yeah, sure. I have a long background looking at understanding human exposure to chemicals of emerging concern. So I suppose it's been the last 5-6 years that we've really been focused on microplastics. And we have a collaboration with the Minderoo Foundation where we are researching how we as humans are exposed to microplastics and nanoplastics, and then what happens after we're exposed. Do they get into our bodies? Do they translocate around our body? That sort of thing. But the first step before we can understand exposure and then potential effects from this exposure is to get the measurement techniques correct. We need to be able to accurately measure so that we know what we're reporting. So this is the first step that we've been working on. How can we improve the techniques that we currently have available to us? So that's where this paper has stemmed from then.
If you could just say a little bit more about why blood. I mean, was it just an easy bodily fluid to come by, or was there some other reason?
Blood's really important because it's the circulatory system. So it is going to transport particles to other organs in the body. So the particle from our normal exposures, where if we're eating plastics or we're breathing plastics, they then need to cross biological barriers into the bloodstream. So the blood's the transport mechanism around the body. After that, then they may be able to enter other organs such as liver, spleen, perhaps the brain. But really we need to understand what's in the blood first.
Yeah, so this is kind of like the first stop for microplastics in the body, and so I guess that makes sense that this is sort of the first stop for your study. So I want to spend a little bit more time than I normally would on your title because I think it's really important. It sets the scope of the research, and honestly, I was really happy to just see your first three words because assessing the efficacy is kind of where I think this field of research is. I've broken your title down, but just by way of introduction into this work. So I want to start with nano and microplastics in human blood, and kind of work back to the full title. So this is a figure taken directly from your paper. And if you don't mind, would you kind of walk us through the important points of this?
Yeah, so I suppose one of the biggest uncertainties that we have in this field is we don't yet understand fully how microplastics and nanoplastics can cross biological barriers in the body. If they do, what size crosses, and then where they can end up in the body. So this is a figure that we produced with the best knowledge we have available to us. And a lot of this is using studies on other types of particles, so not necessarily plastics, but using that to inform what size we think could actually cross, for instance, the gut-blood barrier or the lung-blood barrier, which is the air-blood barrier, and then what concentrations can circulate in the bloodstream, and then what concentrations can accumulate in different organs. So this is, yeah, as I said, best estimate from the information we currently have available. But we definitely need more studies looking at this for the microplastics and nanoplastics specifically. We wanted to produce this image as a lot of studies that are being published now, especially those that are using spectroscopy techniques, are reporting very large particles in certain organs, and it's not biologically plausible for a particle that size to end up in that organ. So we really wanted to show where we think the cutoffs are in terms of particle sizes that can actually get into the body. So this was one way that we could show that through this figure.
Yeah, and the number that really stuck out to me was this 2.5 micrometers, 2.5 microns. It seems to be sort of the largest particle that you would kind of expect in the blood based on, as you said, these are not necessarily models based on microplastics, but just, normal particles that would be able to get into the blood. And then there's various other organs that sort of filter those out over time, even when they do get in there. And then I think it's really good that that's true because I just stole this figure off the internet somewhere. But um, as we know, blood pumps out from the heart in the arteries and it comes back in the veins. But in between there, it has to go through capillaries, as you pointed out in your paper. And those capillaries are only 7 to 17 micrometers wide in diameter, right? So if larger particles did get into the bloodstream, they wouldn't be able to circulate because they would probably get stuck in these capillaries, right?
Absolutely. Yeah, and I mean, there's some blood studies that are reporting particles that are 3 millimeters long. There's no way that they can get into the bloodstream.
Right. Yeah, I saw that. And the only other comment I wanted to make here is that this isn't surprising, right? Because as you pointed out, these models or these numbers are based on studies with other particles, and our body has been dealing with microparticles for since there were humans, right? We've always been inhaling dust and eating some amount of dirt. And so there are insoluble particles that are coming into our gastrointestinal system all the time. And if our body didn't have a way to deal with those, we wouldn't have lasted as long as we did, right?
Yeah, definitely. Yeah.
Yeah, yeah. So in a sense, this is not really a new problem other than it's, a different kind of particle.
Yeah, I mean, and there's a different chemistry involved with the plastic particles, so it's there's potential for them to behave differently. So there's still a lot that we don't know about these particles. But as you said, the body's very good at clearing out particles and protecting itself from these. As if you think about maybe along the road and inhaling soot and emissions from cars, our body can clear a lot of that already.
Okay, so we know that we're dealing with very small particles. If we want to detect microplastics in the blood, then we need to have a technique or a method that can detect those. And so that's why I think you went to Pyrolysis-GC mass spec, and you even state that this kind of technique improves on the size limitations. You mentioned some spectroscopic methods, like I assume you're talking about infrared and Raman.
Yeah, the traditional spectroscopy instruments have size cutoffs of around 20 microns, and then the NaNoRaman can get down to lower, perhaps 1 micron. There are some new technologies that are being developed, such as OPTIR, which can get down to about 500 nanometer. But yeah, really, we went with the pyrolysis GCMS route because we were really focused on the nano-sized particles. They're the ones we're particularly concerned about. They have the potential to cross biological barriers, be accumulated in our organs. So this is why we went with the pyrolysis GCMS.
Okay, and then we go to assessing the efficacy, because the second part of that statement was that some of the characterization information is lost when you go to the mass spec based technique. And then you even point out that the use of this method, you say it's in its infancy, and it's often employed without really fully understanding the limitations. I think this is where the state of the art really is. It's like understanding what methods and finding out which methods can work for measuring microplastic in the body. So, analytical method evaluation. So this has been done forever with all kinds of analytical methods, right? I list 5 sort of categorizations of important evaluations of an analytical method that it really needs to pass all of them in order to use the method with confidence. And I just to compare it, so say we want to know about cholesterol in the blood. There are a lot of ways to measure that. The one, and I just read up on this in preparation for this. I didn't know this off the top of my head, but I've read that the one that we use most often for that is add a mixture of enzymes that generates peroxide, which can you can add another chemical sensor to that, and then you can measure it colorimetrically, and that will give you a measure of how much cholesterol is in your blood. And we can use that measure and look for correlations to behaviors and diet and see what behaviors and diet might give us more cholesterol in the blood. And then we can also look for health effects of that. So additional chance of heart attack, stroke, anything like that. And, we use that to help us live longer and healthier lives, right? So that's definitely a benefit to humanity. But, what we don't do is like take a vial of blood and put it next to our ear and shake it a little bit and listen to see if there's any cholesterol in there, and then just write down how much cholesterol we think is in there based on what we can hear, right? Because if we did studies using that method, they wouldn't be of any value because our measurement is not evaluated, not tested, not validated, right? So that's the difference between a useful method and a not useful method. And so until a method has gone through this sort of validation stage, we don't really know how it should correlate to any of these things that can help us live healthier lives. I'd like to just go through these 5 things with you and the way you've addressed these for microplastics in our blood in your paper.
Yep, let's go for it.
This is a figure that addresses the problem of accuracy. I've mentioned other words that you'll see in some of these overviews of analytical method evaluations, but so things like recovery, measurement uncertainty, and sensitivity are all aspects of accuracy. And I thought this figure summarized what you've done to address the accuracy of this method.
Absolutely. So essentially what this graph is showing is how well our method works at actually pulling plastic out of blood from what we're doing to the blood. So we can't just put blood straight into the instrument. We need to do processes essentially to clean it up. So we do what we call digestion steps. We do filtering steps to separate micro and nano-sized plastics. There's all different processes that happen to the sample before it can go on the instrument. So every time you do a different process, there's a chance you might actually lose some of the plastic along the way. You could lose it to the glassware. So it's really important that for every method you develop, you test how good it is at actually pulling your chemical or in this case, our plastic out of the samples, so you know what's going on your instrument to be analysed. So that's what we say when we're testing the efficiency of the extraction method, how good it is at collecting those plastics. So here, what we've done is we've taken some blood samples We've actually put plastics in them, so we call that spiking plastics in. We've then put the blood through the entire process, and we've measured how much plastic is at the end. So because we put plastic in this, we know how much is in there at the beginning. So by measuring how much is in there at the end, it can see what percentage we got at the end, so what the recovery is. So here what this graph is showing is that the method we have works better for some plastics than for others. For instance, PE is polyethylene, PP is polypropylene. They're the first two on the graph. The recoveries there tend to be higher than a lot of the others. So we know that for this particular method, we're pulling these plastics out of the blood better than we are for other plastics. The interesting thing for this is how it is very polymer specific. So we have different plastics that we're losing to different amounts, and it's all going to depend on the chemistry of the plastic as well. So we're finding plastics that perhaps a little bit more static, such as polystyrene or PMMA, which is polymethyl methacrylate. We're losing a lot more of those. And it also tells us where we need to improve our methods. But it's really important to do this for every method that you develop so that you know how good it is at actually pulling out the chemical or the plastic that you're interested in. You can't just assume, essentially. You can't just assume that a method works. You need to test it.
At this stage of the game, it looked to me like this was not really good per se, but it was probably still manageable. Would that be accurate?
Yeah, agreed. Plastics are notoriously difficult to recover. So if we have the cutoff, and this is for plastics specifically, if it's greater than 50%, then definitely it's manageable. So the more plastic you lose, then the higher your detection limit as well. So if you're losing plastic, then you have to have more in your sample to be able to actually see it on the instrument.
Right.
So once you get below 50%, you really start getting into difficulties there. The other thing you need is you need your recoveries to be consistent. So you need them to be very similar every time you extract a sample, and that's for most of these plastics. But you can see for PET, which is a type of polyester, we have that really big bar. That means our recoveries were highly variable. So PET is not that reliable for in terms of a consistent recovery. So it's one that we'd have a higher uncertainty of when reporting.
Yeah. So the height of the height of the measurement relative to 100 is a measure of percent recovery, and then the width of the bar, I guess, is a measurement uncertainty, right? So you're covering sort of
Yeah,
two
yeah.
aspects of accuracy within the same set of experiments, the spiking experiments. So let's move on down to the next aspect of method evaluation, reproducibility. And this one I think is one that everyone, scientists or non-scientists, can relate to, right? If you can't reproduce your measurement, then it's hard to trust it. I mean, even if you're like doing woodworking or something, there's a common phrase there that you measure twice and cut once, right? The idea is like you want to be sure of what the measurement is. So I think this is sort of universally understood as being important. And I saw that you analyze everything in triplicates. That means you're doing 3 times nominally the exact same measurement. And from what I saw, it looks like in no case were all 3 of the triplicate analyses the same.
No, but yeah, so we take a conservative approach here. Other people might argue it's too conservative, but we at least want to see the polymer detected in all 3 triplicates before we start to be convinced that it's actually there. It's not, say, a contamination from when we were processing the sample. Very difficult though, because plastics are not we use a term homogeneous, which means it's evenly distributed throughout a sample, whereas because plastics, we're looking at a sporadic particle, it's not evenly distributed. So there might be a chance that you take a aliquot of blood that has a particle in it, but then the next aliquot of blood doesn't. So it's something that we need to consider. There's definitely no consensus in the field as to how to address this, how to take a sample that is representative of the whole, essentially. So how do we take a blood sample that has the right number of particles in it? But the best we can do is just by doing numerous repeats of the same sample, so we can try and get a measure. So some people would say if you have a detection, then it's possible you've got a particle there and they'd be okay with that. For us, we're a little bit more conservative and we would want to see that detection repeated so that we can be more confident in what we're seeing.
Yeah, this is something I was going to comment on later, but you're bringing it up now because at this size of a particle, less than 2.5 microns that you're expecting to be in there that are relevant to the measurement that aren't just sporadic contamination, to get to the detection limits that you're talking about, it's going to be tens of thousands of particles per milliliter. It depends on the size and the shape, well, not the size, but the shape and the density of the particle. So, you can't do an exact calculation, but it's not going to be just like 1 or 2 particles per milliliter. It's going to be a lot. So it's hard for me to understand why you would have this sort of sampling error. If you took 3 different triplicates, it's not like you could have 1,000 in one and 0 in the other 2. That doesn't make much sense to me. So I don't really buy that sampling error issue. I really wish more people were doing, replicate measurements.
I think you would have variability in the concentration. So you might have 1,000 particles in one sample and 2,000 particles in another sample. But I agree with you that I don't think you would have that number of particles in one and nothing in another.
Yeah.
So that's why we would expect to at least see that plastic in
Well,
replicates.
and I mean, you're sampling a fluid. Blood is a fluid, right? So if the particles are flowing around in the blood, they're not settled at the bottom, right? They should be suspended in the blood. So I don't know. It's a sampling error thing. I'm not sure I completely buy that.
Yeah, no, as I said before, this is why we do replicates.
Yep. Got you.
Same thoughts.
Okay, so let's move on to range. First of all, thank you for doing this. So you calculate detection limits, which a lot of people do. But the other thing you do is what I call like a reality check. So you say, is it really reasonable that we're going to see this amount of polymer in the blood? And so you take some estimates, and I understand a lot of these are still, just best information that we have. They're not necessarily set in stone. But you say, okay, so an absorption efficiency up to 1.7%, half-life of about 12 hours. You calculate that you would need to inhale or ingest about 6 milligrams per day just to meet the minimum threshold. And I calculated that myself. I got the same answer. But the thing that you didn't include explicitly in the calculation here is within the right size range. You did state that elsewhere. I put it in brackets here because you didn't say it in this particular sentence, but you did mention it. What I do in these YouTube videos is I give the peer review that I would have given if I had gotten this paper to peer review. And I would have said publish with minor changes, and this would have been the minor changes. I would have asked you to elaborate on this right size range, because I think a lot of people don't realize the right size range, if that's 300 nanometers to 2.5 microns, which is what you would be able to detect after your filtration, assuming the upper cutoff of 2.5, that's 0.00024 weight percent of all microplastics up to 5 millimeters. So it's really a small fraction of what we inhale and ingest that would come into our body, into our blood, not into our body, but into our blood. And if you multiply that by 365 days and 8 billion people, it turns out that your annual microplastic human ingestion would be about 100 times the annual polypropylene production. So it's really just not reasonable at all that you're going to get into a range that you can measure based, assuming that all of these assumptions are correct and the assumptions that I made in giving you those calculations are correct.
Yeah, that's an interesting calculation.
I want to actually elaborate on that even further. So I took your numbers, and this is what I love about science. This is why I really prefer reading papers that teach me something, because when I learn something, I can use other things I learned from other papers and put it all together and then really learn something completely new. So I took the numbers that you gave me in this paper, half-life and absorption efficiency, and then I used this alpha from a recent paper that showed that there are a lot more of those smaller particles than was originally thought. So this is a bigger number than what I had been using in some of my previous videos. So this is based on some other research that I felt like taught me something. And then I used this annual intake of zero point 0.2 milligrams per year from the NOR review of intake, which still is the best one I've seen. I tend to think this is on the low side. It's way lower than everyone seems to think it is, but I still haven't seen a better estimate than this. And this is the median, okay? So this isn't like maximum, this is the median. If you put all of those in, you come out with a steady state concentration in the blood of 3 times 10 to the minus 12 micrograms per milliliter. So that's like 10 orders of magnitude less than your minimum cutoff. So you're way out of range for the average. And again, all of these numbers could be wrong, but this is my best estimate based on the best information that I could find. So the only other thing I did, I added a high intake case. He gave like a 90% certainty, a high end estimate, which is a lot higher. So it's 31 grams per year. So I put that in, and median, that means half the people are above that. So, could you see something for some people if some people were taking in way more than that lower estimate? But even then, I only get up to 5 times 10 to the minus 7. So it's still like 4 to 5 orders of magnitude less than it looks like this method's able to go to. So, based on this and based on your lack of reproducibility, I mean, those two are really consistent with each other, right? It just seems like
Yeah.
this method's just not going to get you to the range that we expect for the concentrations.
Yeah. And yeah, that was one of the conclusions of the paper, that the techniques we have are probably not sufficient to be able to see realistic concentrations that are getting into the blood or into the organs. And we need new technology, we need new developments. Yeah.
Yeah, and I think that's why this is such an important paper because you save people a lot of work doing this kind of evaluation of the analytical method beforehand. It I think can save a lot of confusion down the line if people understand that this method is just not going to get us reliable results for microplastics in blood. Okay, so selectivity, this is where I think your paper really distinguishes itself because I think what you've done showing how to deal with interference or identify interference, I would say, is really important. So maybe just by way of introduction, I want to give like an example of interference would be if someone hands you a glass of water and says, I think there's some corn syrup in this, right? And so you take that glass of water and you say, well, I know how to test for corn syrup. I want to see if it tastes sweet. So you take a swallow and it tastes sweet. And so one thing you could do is say, well, that's a valid test for corn syrup in the water. So it's sweet, therefore it must have corn syrup. But you don't really know that, right? Because it could be sugar, it could be saccharin, it could be sucralose, it could be NutraSweet, any of these other things. And so that would be an interference for corn syrup, right? And there's a lot of other research groups, I think, that are just sort of tasting the sweet and calling it corn syrup when it's really sugar all along. And Guys like me that are chemists that, look at these kinds of things have said, look out, I think you're actually measuring something other than what you think you're measuring. And that only goes so far. And I think this is what really is the most important part of your paper, because you're saying there's an analytical method, there's an analytical treatment you can do to tell whether you're measuring what you think you're measuring. So I'll shut up now and let you explain maybe how you work your magic here.
Yeah, so this one's a bit more complex, this concept. So as you were saying, in this case, when we're using the term interference, we mean something that's giving us a false positive. So something else that's in the sample that is giving us a signal for plastic. So if we're not looking at the data properly, we can go, oh, there's a peak, we have a plastic, when it's actually something else that's given us that same peak. So the real challenge with this analytical technique, Pyrolysis-GC, is that it's an indirect technique. So you're not actually measuring the plastic, you're measuring a breakdown product of the plastic. So then by measuring those breakdown products, you can back calculate out the amount of plastic that was in the sample. It's impossible to, well, not impossible, but with the Pyrolysis-GC, it's not possible to put a solid plastic onto the GC. You need to break it down first. So in this case, if you have something else in your sample that also breaks down into that same breakdown product, so that same chemical, you're looking at the same chemical. You're looking at exactly the same thing. There's no way to know what its source was. So you don't know if it's, so the example we use here is polyethylene and then also lipids. So lipids, when you decompose them, when you pyrolyze them, which means you burn them, you break them down into the same small chemicals that polyethylene breaks down into. So when you see this small chemical in your analysis, you don't know if it's come from polyethylene or if it's come from lipid. It's the exact same chemical you're looking at. So this is the biggest challenge with pyrolysis, is to try and not have these false positives. So what we found is that because lipids, the original structure, is very different to a long chain polyethylene, polyethylene breaks down into a series of small hydrocarbons. But the ratio of these hydrocarbons that it forms is very different to things like lipids. They will form, like the lipids, because it's smaller, it will tend to form more of the shorter hydrocarbon chains rather than the longer ones. So by monitoring these ratios of how these products form can give us an idea if we're actually looking at polyethylene or if we're looking at, say, a lipid instead in the sample. So this is a bit of a complicated graph here, but that's kind of what it's showing. So the first graph is showing blood that we have spiked with polyethylene. So we put polyethylene particles in here so we know there's polyethylene. We're looking at the ratio of those small breakdown chemicals that it forms, and the red box is really the uncertainty. So if all of those blue dots are within that red box, then we're pretty confident we're seeing polyethylene. The graph on the right shows a normal blood sample, and all of those blue dots are not inside that red box. We have some that are close to the top and a lot that are underneath that box. So this means we're forming different ratios of these breakdown products. So this tells us that we've probably got some lipid that's still in that blood sample. We don't actually have polyethylene in that blood sample. So we know interferences, and this propensity for false positives is a huge issue for Pyrolysis-GC. So as you said, one of the things we wanted to do was to develop a way to assess the data so that we know if we're looking at a plastic or an interference. And so this is one of the techniques we've developed for that.
Okay, so a few additional things about this graph. So I guess to compare it to my simple analogy earlier, maybe this is kind of like a flavor profile, right? So this is the flavor profile of actual polyethylene on the left, and you can see that there's some aspects of that are not within the expected range, and so you know that it's not actually polyethylene, right? You don't necessarily know for sure what the interference is from by this experiment, but in this case, we're pretty sure it's from lipids that are normally in the blood, right? So we're talking about long chain carboxylic acids and long chain hydrocarbons, waxes, that kind of thing that are normally in the blood, and that's why that experimental procedure you mentioned at the beginning, people are always looking for ways to remove as much of those lipids as they can so that they don't have this interference. And in fact, that's kind of what I've seen in a lot of papers is they'll say, we know about these lipids interfering with the polyethylene, but we've used an isolation method that we hope and expect to remove the lipids, so we don't have to worry about those. And again, I'm a synthesis guy, so I can look at their procedure and say, yeah, you can hope all you want, but you shouldn't expect that you're removing all of them. It's really, really hard to remove them all.
I will also comment on that. I'll just jump in. Also, in
Yeah.
science, you shouldn't expect, you should test. You should never assume that a method has removed a lipid. You should test it, extract some lipid with your method and see that it gets rid of the signal. But not many people are doing this. As you said, they just assume that their method is working. And we've shown that it often doesn't.
Yeah, that's exactly. I'm 100% online with you, and again, that's why I think this is such an important paper because I didn't know how to do that. Now I do, right? You've shown the world how to do this, and you say not many people are doing it. I mean, my experience reading this literature is you're the only ones. I mean, this is the first and only paper I've seen that you're doing it, and I'm really hoping that people read and understand this paper and apply. Um, this method to what they do in the future. And hopefully we can start to get some more reliable papers coming out in this area. The last comment I wanted to make here is this interference is a really diabolical problem because you can trick yourself into thinking you have an excellent analytical method, right? You can make yourself think that you're passing everything, but you're really measuring something that you didn't think you're measuring. It's just like that taste test for the corn syrup, right? Hey, I can taste it for sure. It's sweet. I know it's good. I can even quantify it. I know that it's working, but you're fooling yourself if you don't think of the other alternatives of what it might actually be.
Absolutely. Yeah, definitely agree.
The next thing I have on here is robustness, and I wanted to include that because it's in most of these summaries of what you need. And this would be making sure that your method works for all types of analytes that you might encounter. So all different blood types, you would look at like a range of, say, cholesterol levels, protein levels, that kind of thing, and make sure that your method worked across all the types that you're using. Now, of course, if you don't have sort of a working method coming into this, there's really no point in doing this. So I didn't really see anything in your paper about this, but there's really no way to address this at this stage, right?
Yeah. Also, there's so many variables, it's hard to know what to test as well. Like you said, everyone's going to have a different makeup of their blood. How many different bloods do you test? Yeah.
Yeah.
It is something I've been discussing here and something that we've been discussing. Should we make a pooled blood sample of many different people and then use that for various tests as well? So it is something we've been considering. But yeah, as you said, yeah, it's kind of the last thing that you would do once you have a method that you're really happy with and it's passed all the other criteria.
I guess in summary, what I got from this paper is accuracy was, not exemplary, but probably workable with some corrections. Reproducibility just wasn't there. The range, especially after when you account for the size that you expect in there, you just aren't going to be able to detect the amounts that we expect to be in the blood. And then the selectivity also is not very good because you have all this interference with certain polymer types. Other polymer types, it might be okay.
Yeah.
Is that a fair assessment?
Yeah.
And then
Yeah.
I think the most important thing to take from this, and you do mention this, so you list, I think, 16 references where you comment that especially when it comes to this interference problem, that it's not clear that all of these other papers are really thinking about that or accounting for it properly. And I couldn't agree with you more. I mean, I just feel like a lot of medical researchers are out there using this method as if it were the enzyme plus colorimetric method. And really, it's the hold it next to your ear and shake it method. Because the numbers that they're getting using pyrolysis-GC mass spec are really no better than that. I just don't think they have any value at all. And it's a shame to see so much uh, excellent work go into like getting the questionnaires out, getting the samples prepared, trying to correlate with input variables and output variables, health outcomes, and all that kind of stuff. But if you don't have the central measurement correct, if those numbers are not reliable for microplastics in all of these different organs, which they aren't, all that other work is not any good. And again, that's why this is clearly the most important paper in this field, in my opinion, because this is a bombshell. This is really forcing us to reevaluate everything we think we know about microplastics in the body, which is turns out is really not very much.
Yeah, there are still papers being published that are not doing the quality control checks that we've suggested in our paper. So it's a little bit frustrating, but we're definitely trying to get the word out there, and we're hoping that it can just give people an idea of how they should be quality control checking their data a bit more before reporting, especially manuscripts that are reporting very high concentrations of either polyethylene or polyvinyl chloride. They're the two that really do suffer from interferences because they don't have specific breakdown products. So they're the two that you like really need to be second guessing any data that you get from those and quality control checking the data. So we're hoping that, yeah, with this information, we can start to get other researchers to understand this and start to implement these methods.
Yeah, and I think the most critical one that you've pointed out how to address is the interference, the selectivity. But some of these papers really, well, as I mentioned, I hardly see anyone even trying to reproduce their results. And especially if you look at range, like, okay, so I would summarize it this way. A lot of these papers are making really extraordinary claims, and they're not bringing even ordinary evidence, right? Because they're not doing these analytical method validations that you have to do, that you really have to do to even provide ordinary evidence, right? And if you look at the expected amounts of microplastics based on biological models and what we know about intakes, or what we can estimate about intakes at least, the numbers that they are reporting are much, much higher in almost all of these cases than what's expected. Now, that doesn't mean they're wrong necessarily, but it means that there should be a very, very high bar for the analytical method validation that they're using. And there should also be some sort of an explanation for how they think there can be that much in there. So what do they think is wrong about the biological models that we're missing that allows that much to get in there? So it's just so many of these extraordinary claims, and they all reference each other and make it sound like, these are all, just sort of normal now. And it's almost like a cancer that's sort of growing in this area of research, and it just needs to stop. We really need to cut this out. I honestly, and I say this without joy, I say this without exaggeration. This field of study would be better if we would just take all of the papers about microplastics in our body and get rid of them and just start fresh, because there are so many bad ones out there that they're just choking out the good ones that are really well thought out and really starting to come in and starting to make sense of this.
Yeah, and just to add on to your point as well, a lot of these studies are trying to draw correlations with certain health effects, and you can't do that if your data is not good. So if you're reporting false positives, but then you have a health effect with, say, increase the earlier mortality, or a horrendous health outcome, but your correlation is false. That doesn't work as well. So then you're also causing undue stress to
Just
people. Yeah,
shaking it next to your ear, right?
yeah, yeah.
Yeah.
And it's irresponsible as scientists as well. If we want to be able to get the data right so that we can properly inform our health agencies, our governments, the general population.
Yeah, well, thank you very much for this paper, and congratulations to you and your co-authors. This is just an outstanding bit of work, and I appreciate it. I think the rest of the scientific community that is really trying to get to the truth of the situation hopefully appreciates this, and I hope that this kind of alters the trajectory of the research that's going on in this area.
Well, I think we've covered everything really well, and yeah, appreciate the opportunity to be able to discuss this in more detail as well.
I really appreciate having the discussion. It's more fun for me, and I'm all about. I know you're about like solving health problems. I'm just a geek. I just like good science. So anytime I can read a good scientific paper, anytime somebody teaches me something, I'm happy. So I really appreciate the discussion. So thanks to you and to all of you who are watching and learning along with us. Thanks for watching, and there's more to come.